I think you're going to like today because the math is a lot easier. We're still talking about kinetic equations and things for reactions, but man, you're going to see the math is so much easier. Okay, what is the difference first between an elementary reaction and a reaction mechanism? Remember writing down those words? Kendall, you remember writing this stuff down? I think, what's that? Jose's? Jose's just, yeah, what's just one step? The elementary reaction, just one step. Very often, we write, I should Google one of these. I got to look that up. Very often, we just write reactants, go to products, right? Just blob, go to blob. We don't really know how it gets there. It's almost like a black box. Something happens, these reactions get converted to products. Well, if it's one individual step, this molecule A actually colliding with this molecule B to make molecule C, and you know that's all that happens, they call that, like Jose said, an elementary reaction. But if the case is really, no, A has to collide with B and make C, then you have a second step in all this. C has to collide with A again, and then you get D. Your overall reaction would be what goes to what? What would you cancel out? Cancel out the... Well, the A's aren't going to cancel. They're both on the reactant side. Cross out the C's. So you cross out the C's. So your reaction is really how many A's? 2 of them plus a B yields D. This is what we're used to using. We're used to seeing. We never realized how it got there. So 2A plus B goes to D. But this never really happened. You never had 2 A molecules at the same time colliding with a B molecule to make D. No, that never happened. But this is what we use all the time in all of our chemistry problems. Okay. So that's what we're talking about today is somebody went out and they had to use picosecond spectroscopy or something that's really, really fast to detect these ultra-fast steps and recognize first this happens, then this happens. Okay? So a reaction mechanism is all these steps. Add them all up, cancel out what you can, you get the overall reaction. And this is what we've been using all the time. So these individual steps are what Jose called elementary reactions. He's right. Some more terminology. What is the molecularity of each elementary reaction in the above mechanism? So we have step 1. What would you guess, Enrique, is the molecularity of step 1? What would you guess? Looking at what's going on in that step, the number of molecules involved is what? To get it to go.
To get to what?
To get it to go, to get it to happen. You need how many molecules to collide at the right orientation, the right energy? Yeah, 2. So that's all they're saying. It's a fancy way of saying you need 2 molecules to, well, molecularity is the number of molecules that got to collide at the right orientation, at the right energy, and man, then you'll get it to happen. So for step 1, it's just 2. And that's really what a catalyst does. Is a catalyst, it grabs onto one of those reactants and holds it in the right orientation. So all these collisions that are going on, man, it's much more efficient. It's going to happen much more often. And that's really what it's doing. Step 2, everybody. The molecularity is 2 again. Okay. And you can't refer to molecularity for the overall reaction because that's not an elementary step. It doesn't make sense. So molecularity is only referring to elementary reactions. And how you know if it's an elementary reaction? Well, you pretty much have to be given this entire reaction mechanism, right? Because that's what all these elementary reactions are. They're these individual steps. So how do you write a rate equation for an elementary reaction? Okay. So if we're going to write a rate equation, Steph, in the first place, we always write something equals something. Yeah, that's how you start. Perfect. Okay. Now, Kendall, I already picked on Kendall, I guess. I'll pick on her again. Kendall, today you're going to like. What would you love to write as the rate law for this step A? Rate equals K times what? And I bet you're going to say the right answer. What would be the easiest thing to say? Rate is going to be K times what? In brackets. And remember, they always have to have some power. What power would you guess up there? 2. That's the rate law. So this is so much easier, right? Before we had to do experiments and calculate this stuff out. Now all we do is look at the elementary step. You can immediately write the rate law. So nice. How awesome is that? How would you write the rate law if the elementary step, the elementary reaction, Megan, looked like this one? What would you write? What equals what? Rate equals K brackets D to the 1, C to the 1. And I guess if we want to could write, this guy's step 1, step 2. They're going to be different K's, but that's the idea. Okay. Writing overall rate equations for a reaction. Okay. So we talked about how to write it for individual steps, but how do you write this for an overall reaction? Okay. So here's a reaction mechanism. And you have 2 steps is all that's involved, but one step is super slow. If we know how to write the rate law for each individual step, can we say that one of those rate laws will be the rate law for the entire thing? The first step is really slow. So once the first step happens, you generate some C, boom, you get your D and you're done. It's like a bottleneck, step 1 is. The entire rate is pretty much tied up in what step? In step 1. So step 1 is your rate law. You're done already. You just write the rate law for the super slow step, and you're done. So the rate law for this entire mechanism, we could have a bunch of steps in there, Jose, but you pick out the slowest one and write its rate law. So the rate law for this would be what equals what for this mechanism? Rate equals K A. Yeah. And you're done. Today's a lot easier stuff, I think. I don't know, comparison. They're giving you a break, I guess. Too bad it's not a Friday. Catalysis. What's the difference between a homogeneous and a heterogeneous catalyst? If this thing would have worked, right, it's supposed to be detecting hydrogen. Okay. And you see the material, it was this solid, right? Ooh. It's turning darker now. Well, I mean, it's just because the room's dark. But, man, I swear it's blue now. Doesn't it look blue to you, Jose? Shit. It is blue. Kind of. Man, that thing, it's got more issues than just heating it. It was super slow. It's definitely darker now. Anyway, okay. It's a powder, so the sensor is a solid. It's detecting a gas. Those are 2 different phases. Which word meant different, hetero or homo? Hetero did. So this catalyst in here, which I can't tell you what it is, even though it isn't working very well, because maybe I can get it to work someday, right? That's got to be a heterogeneous catalyst, because it's a different phase than what the reactants are. So homogeneous and heterogeneous catalyst just means, hey, well, what phase are the reactants? If the reactants are all a liquid, and your catalyst is a liquid, Well, then that would be a what catalyst? Homogeneous, right? It's in the same phase. Okay. So let's see if we can answer a few questions. We might get out of here early today, right? Go ahead and write down the molecularity of each reaction here. Write down the molecularity of each reaction. So what'd you write, Audrey? This one would be, you can tell, it's count them up. Well, only the reactant side. 3, 2, 2, and 1, right? Not bad stuff. Write a rate equation. And they show, I mean, they make the question with more verbiage than it needs to be. The point is just write the rate equation. Well, of course, rate equations have dependence on concentrations. That's how you write a rate equation. So Connor, what did you write for A?
Rate equals A bracket CS2.
Yeah. Hey, how do you name CS2? Carbon. Ooh, man, you remember carbon disulfide. You see Kendall. Andrea, how do you do B?
Rate equals A and then brackets CH3BR and then brackets
Yeah, methyl bromide and hydroxide. Not so bad. Okay, I think this question's a little more interesting. Here's our reaction. Okay, and they gave us the rate law. And they give us a solution of these reactants, right? The things that are in there. Let's see if you recognize something here first. Mia, do you recognize what this is? We hardly ever write this ion this way. We always wrote it as something else. Do you remember? Hydroxide was OH minus. Does anyone remember what this was called? Hydronium. Hydronium. And we never wrote H3O plus. We always wrote what instead? Give you a hint. You add this to H2O when you get hydronium. H. We always just wrote this, a bare proton. But they believe these bare protons in water react with water, and you really get hydronium, H3O plus. So we're technically should be writing H3O plus always instead of H plus, because that's technically what they believe is going on. But you get the same chemistry and the same answers, same predictions, just by writing H plus, and it's easier. Okay. So that's really just so that you recognize that. H3O plus is the same thing as H plus. They're exactly the same thing. They're exactly equal. Okay. So they're telling us the concentration of that compound, good deal. Then they said 0.15 molar HCl. Alyssa, what's that doing there? I can't even ask Kenneth anything. Kenneth, you turn anything in? I'll ask him next time. Alyssa, what's this 0.15 molar HCl doing there? Right, they told us the concentration of one reactant, HCl, do you remember it? It was a what acid? It's hydrochloric acid, and it was really concentrated, really yeah, soluble? Well, we never really called it soluble. Strong. But soluble is the same thing because it means it breaks up completely. So soluble and strong means the same thing. But yeah, it's really strong acid. So this really means that you have 0.15 molar H plus because it's a strong acid. So a lot of times my brain doesn't even see the chloride because I know it's a strong acid. So I see 0.15 molar H plus there. Okay. Anyway, that's just looking at the question a little bit, probably more than we needed to. But for each of the changes listed below, state whether the rate increases, decreases, or remains the same, and then say why. So what we're going to do first, Kenneth, what we're going to do first here is we're going to add some sodium hydroxide. Heck, I don't even see NaOH in the rate law there or in the reaction. Is that going to have any effect? No. First guess, I would say no, but then you got to look at it more. It will. Steph? Yes, the OH is going to neutralize the H, right? Because remember, hydroxide and H plus make hydronium or water, right? They make water. Hydroxide plus, right? A base and an acid make water. So if we're adding hydroxide, we're actually doing what to this number right here? It's not 0.15 anymore. It's going to go up or is it going to go down? It's going to go, somebody said it, down. It's going to go down because this hydroxide's reacting with it. So you're not going to have 0.15 molar. You're going to have, I don't know, it's going to be lower. That's the whole point. It's going to be lower. Well, if that number's smaller, if that hydronium ion concentration in brackets, if that's not 0.15 anymore, it's lower, well, then the rate's going to go down. That's the game you're playing. So take a look at each of these and see if you can make a guess. Try to guess each one of these, B, C, and D. Take a look at them. See if you can make a guess. And then we'll see if we can come up with consensus. You can ask folks around if you want. Man, that's definitely darker now. I think it worked. It's just really slow. I don't remember it being that slow. Right? Does that look darker than you remember it? You remember seeing it the first time, Kenneth? It's darker now, right?
Yeah, a lot.
Right? Yeah. It worked. You guys believe me now? Will you give me $1 million for this? It's darker now. See it? Now you believe me? This would work. It's just, I don't know, someone has to heat it up, and then it's really slow, too. It might go boom before it changes color. But it works. It's better than nothing. Let's see if you can get answers for these. Enrique, what do you think for B?
I think it stays the same.
You said stays the same. Everybody agree? Add some water. Right? Water's not anywhere. It's like adding iron. Doesn't do jack. Does everybody agree?
Yes.
I would until I realized something. How do you, if you add, you're changing molarity. By adding water, you're changing molarity. And you're changing that molarity. Are you making that molarity? Molarity is like right now 0.15 molar and 0.2 molar. Is that number, is that molarity going up or is it going down by adding water? It's going down. Well, if it's going down, the rate's going to go down. So that's the trick to doing it. Shoot. Megan, we're adding a catalyst. Hopefully a catalyst that works. The rate would increase. So an effective catalyst. Okay, now we are carrying the reaction out at 15 instead of 25. So I guess you made it colder. Andromeda, what would you guess? Making it colder. Decrease. Yeah, things slow down, right? I guess you got to be careful because if they would have said endothermic or exothermic up there, you'd have to read that, but they didn't say anything. So in general, you have to just assume, hey, it behaves like most reactions. They're going to slow down if you make it colder. Okay, only one last question. Draw a potential energy diagram for an uncatalyzed exothermic reaction, and then do something on your plot that shows the addition of a catalyst. I think we answered that at the beginning of class, right, Cameron?
Yes.
So what are your axes? What's your y and your x axis? Potential energy. Reaction coordinate. So Cameron, reactants go to products. Reactants, so at the beginning of this reaction coordinate, I have my reactants. Reactants, really high energy or really low energy? If it's exothermic. Where would you draw it? Really high, because you got to end up really low. Good. So draw reactants way up here. Draw products down here. And draw a hump between them. Right. So there's your energy of activation. Here's your delta H. Didn't ask for that, but you catalyze it, and then you just change what? Change the hump. And say that's catalyzed. All right. So have a good day.